Okay, so homework for today was the Dijkstra's algorithm, right? Taking the pass through our towns, and remember last time we took a look at Dijkstra's algorithm following our roads here. So we have a queue of nodes we haven't visited. We do have to pre-pick a starting town in our case. I think, didn't we do an example here? So I think we picked Mequon as our starting town, so you can tell whether this gave you the right thing. So we're going to pick a starting town and then go through and effectively process Dijkstra's algorithm for our entire graph given that starting town. So Dijkstra's algorithm, the ultimate goal of it is to fill out your graph with some additional pieces of information. That is the lowest cost and where you came from to get to this place. In our particular case, all our roads are two-way roads. So we don't have to deal with a situation like this where it's 9 in one direction and 2 in another direction. We don't have that world in ours. Okay, so the first thing we need to do is we need to make sure first thing we need to do is we need to make sure that we go through all of our potential towns. All right. Now, we do probably want to have the ability to get a town from our town collection, because remember, our town collection here, a town collection is an array of towns along with a count. Actually, we did it as an object. We just showed structs there. All right. And we have the ability to get a town by its name. So that'll allow us to get a specific town. So for us, these are all of our town names. So we're going to go ahead and get our starting town. Where's Maine? All right, so we'll go ahead and create a town pointer, starting town, and we want this to be our town collection, get town, and we'll give it Mequon. That's going to be the town that we're going to start with. All right, we're just flagging that guy as that. All right, now we want to go through every single town in our town collection. That's going to be our queue of towns, right? So we're going to do something for every single town in our town collection. So for int I is equal to 0, I is less than town collection. And did we make these guys public, private? Did we give ourselves a getter? We made them public, so maybe not the best idea in the world, but town collection count I plus plus. All right, because remember, the purpose of our town collection is to hold an array and the number of things in the array, because in C++ arrays can't hold that information themselves. All right, so this is my starting town for Dijkstra's. Now I need to go through my entire queue of towns. All right, so this goes back to our picture here. This is all the towns on our map, including our Mequon, right? We've decided that Mequon, making the connection here, that Mequon is our starting location, but all the things that we're going to visit are located in there. Okay, now, so we're going to do something for each of those towns. So I can go ahead and say town pointer per town. And then in here, I can go ahead and say cur town is equal to town collection, the towns at bucket I. And that's what I called it in there, right? Called it the towns. The towns is the name of my array of town pointers. All right, so go through all the towns in my town collection, go ahead and grab the current town, and then we're going to do something related to that current town. All right, going back to our picture here. We've now extended what a town is in our world. We need to give two additional pieces of information. One's going to be the shortest distance, whatever we want to call it. The other one is going to be a where you came from to get to that place. And for us, maybe we say that this is a string and this is just the number. So maybe we represent infinity with like a -1, and we represent the place you came from as a string, and maybe initially it's the empty string. Okay. So we need to go and add a little something to our town objects to keep track of some extra information about those. So we'll go to town HPP. So no longer do we just have town name, a collection of roads, and the number of roads in the collection. Now we're going to also have a int shortest distance, to say that. And we're going to have a string shortest path predecessor. I hate spelling that, but it's probably about the correct name for it. I don't even know if I spelled it right there. Is that right for predecessor? We'll soon. So I'll take those two variables, and inside of town CPP, in our constructor, we'll go ahead and initialize shortest distance navigation capsules. What does that even mean? My watch just said there's no navigation capsules. I don't know what that means. All right, so shortest distance we'll initialize as -1 here. That's going to be our placeholder for this infinity symbol here. So as long as something's -1, we know we should ignore it and this guy automatically wins, something like that. Alternatively, you can make it some gigantic number and just hope that your first pass through is smaller than that number. Because if you remember, we're comparing it, we're looking for minimal values. So like for instance, when we compare right here, we're going to say, well, which is better, a 7 or the 3, 4, 5, 6? So we'll replace 6 is less than 7, so we'll replace it. Well, let's assume that we put a maximum value of 10,000. That was our starting value. We just figured, oh, that's safe. If we put 10,000 there, it's big enough. Well, what if you happen to have distances that were 10,003, something like that? Then you wouldn't be able to rely on that. So if we just treat -1, which we're going to say that's an impossible distance, right? We treat -1 as our infinity thing, then we could just check against that special value. All right, so we'll start that off at -1, and we'll start shortest path predecessor equal to the empty string, knowing that this guy is going to get filled in the very first time we go ahead and replace that. Unless there is no way to get to a town from our starting position, which potentially could happen, right? Our graph doesn't support that. In our graph, you can get everywhere from all of the towns because we've created, I guess, what I originally had advertised as a full graph. You can get to all the places, but nothing about a graph data structure says you have to be able to get everywhere. You could hit some dead ends. Okay. So now that we've added some abilities to those guys and we made them all public, which is a little bit crappy, but for time, that's gonna make our life a little bit easier here. We want to go through every town in our list and compare that town to the thing that we're trying to get to. We're going to go through all the roads for that town, whatever the current town is. So for each town, I'm in town there. Now we need to go through all of the roads for this town. To see what we need to update. All right, so to remind us, we go back in here. We started off with this is our base. Everything had infinity symbols. We had our unvisited queue. There is no guarantee that the first town we run into in our queue will be our start town. That just happened to be the case in this example. All right, so we start processing A. So we go to town A. This would be Kerr town in our example here. So my code here, I've set Kerr town equal to the current town we're looking at from our queue. All right, so this would be Kerr town. And then what I'm going to do is I'll ask the question first, is this town my start town? If it is, I can go ahead and set this guy's distance to 0 and set his, we can just leave his start location to the empty string. The distance to your start town from your start town is 0. And it's always going to be 0. And you didn't come from anywhere to get there. Right? So we can treat that as a special case. So we'll go ahead and ask the question, if starting town is equivalent to Kerr town, just going to compare the pointers, the memory addresses of those guys. If that's a true statement, we will set. Yeah, you guys were really still for the last. We haven't had that happen in a while. That happened in my grad class last semester. Like people just didn't move enough because the lights are on like a motion detecting thing. I should be able to force it back on, or maybe just me moving. Well, all right. So if my starting town pointer is equal to the same thing as the Kerr town I'm looking at, then I'll go ahead and set starting town. What did I call it? Distance, something or other. Shortest distance. Let's just go look it up. Shortest distance. Equal to 0. And we'll just leave the starting point for our where you came from to the empty string. It's not going to hurt anything. Okay, so we'll do that if this is our starting town, and we should only hit that once, right? So that'll just be our placeholder. So going back to this, we dealt with our starting town. Now, from this town, we're going to look at all the roads leaving that town. Okay, so we're going to have another loop that's going to go through all of the roads within the current town. And that's a road collection, right? Isn't that how we represented it? Oh, actually, I think we represented it inside of town. Yeah, town has a collection of roads, and it has number of roads in a collection. So what we'll say here is we're just going to have another loop for int j. Actually, what we can do here is we can say for int j is equal to 0, j is less than Kerr town number of roads in collection, j plus plus, and we're going to need the current road for this guy. So I'll go ahead and just give myself a road pointer up here. Kerr road. And then in here, I'll set Kerr road equal to Kerr town dot, what did I call it? Collection of roads at bucket J. So that'll get the road that I'm currently looking at. All right. Okay, so for each of those guys, what do I want to do? I want to see where it leads, right? Where it leads out to, and update the value at those places. So leading out, so if I just go through, so this is bucket 0, this is bucket 1, let's just say in our example. So bucket 0, it leads to a destination town. If you remember, what's our road? Our road keeps track of 2 towns. The town we're currently at, presumably, and the town we're going to. So we need to get the town that's not us. All right. So maybe we teach road, get destination town, given our town pointer per town. So if I give it a cur town, I give it the town I'm standing in, I ask a road to tell me the destination, it'll check to see which town is not cur town and give me the other guy. That's where it's going to. I'll just give an ability to a road. All right, we'll just make a guess. We'll say town pointer answer is equal to this T1. Then we'll say if this T1 is equivalent to cur town, well, we could say this T1 or we could say answer. I'll stick with answer. So if answer is equal to cur town, then we're going to say answer is equal to this T2. And then return answer. So we'll take a guess. We'll say the destination relative to the current town is town 1. But if I happen to already be in town 1, switch answer to be town 2. And then spit that out. All right, so this function will return the other town other than this guy. Hence the destination. Okay. So I built that in there. All right. So now we want to go through all of these roads that are inside of here and grab the town that is at that destination. So we'll give ourselves another town pointer. We call this guy Desk Town. The Desk Town is equal to cur road get destination town given per town. I'm currently in this town. I have found this road that leads out of that town. Give me the town that that road leads to that's not me and store it inside of Desk Town. Okay. Now is when I ask that question. I got to decide, do I update that town's information or not? So going back into here, initially, by this example, my town B, in this case, is going to have a distance of -1, which means I automatically update it. Okay, so I do need to ask about that special case. I got to say, if my desk town's value, if my desk town's shortest distance is equal to -1, then by default, this is the first time we visited there, we have a new winner. If desk town shortest distance is equivalent to -1, then I'm going to go ahead and set desk town's shortest distance equal to the cur roads distance. And then I'll set desk towns shortest path predecessor equal to per town. Oh my gosh, you're just sitting in the dark. Deal. Do we still see okay? Like is this acceptable? I wonder why it's doing that. Per town. What's the town's name? Town name. Oh, those are all private too. So we need to get town name. Oh, I'm dealing with all those. What did I do in road? That was a bad citizen in road. So we're going to just be a bad citizen in town as well. Again, for time purposes. So now I can directly access town name. So destination town shortest path predecessor, if I'm updating the shortest path to get here, is now my Kerr town's town name. Okay, but that's if the current shortest thing is a -1. The other way this would happen is if my Kerr road's distance is less than my, well, let's see, if my Kerr town's distance plus the road's distance is less than the place that I'm than the shortest distance at the current destination town. So if I fast forward down here so we can see it, when I went from A to B, then B to D, and then D to C. This is 3 plus 4. Now 3 plus 1 gave me a 4. So this guy has a 4 here. So I'm checking if the current town's distance or current town's what do I call it? Shortest path distance or something like that. Shortest distance. If the current town's shortest distance, this guy right here, 4, for example, plus the road's distance, which is a 2 in this case, is a 6. If that's less than the destination town's shortest distance. Make sense? The math problem we're asking here. So if this is true, or my per town shortest distance plus my Kerr road distance, if those two things added together is less than my destination town shortest distance. If either of these things are true, this is either the first time I'm visiting this town from anywhere, or the total distance leading to this town, including this road's distance, is less than my previous best distance to get there. If either of those things is true, we're going to update the information on that destination town. Make sense? Okay. But we're only going to do that if we should update it. So that's what we'll do. If I'm looking at this guy for a second, I'll do that for this road here. Then I need to do it for the next road. So I need to do that for each road coming out of the current town. And that's what my inner for loop is for. This says for each road coming out of the current town, ask this question. Should I update the destination town relative to this guy? Okay. So once that's done, I will have visited, I would have looked at this road, I will have looked at this road. So now it's time to loop back up and get my new cur town. Work through the queue. Okay. So what I want to do here now is I want to teach. I already have a display method for my towns. And right now my display method, I show roads leading out, yada, yada, yada. Let's just write a second display. We'll do a avoid display Dijkstras. I think I spelled that right, maybe. Let's just call it good. So we'll teach him a Dijkstra's display where we'll have the town name, and then we'll have the distance and the previous town. That should allow us to check our work against what we have here. So we will implement this guy. Okay, and we'll go ahead and write out, here's the name of this town. And then why don't we go ahead, I won't even do an end L yet. That. And then we'll do a C out, open parenthesis, this is the shortest distance. And this shortest path predecessor. Close that parenthesis. And end L. So when we display Dijkstra for each town, we'll just have it show the town name and those two pieces of information. The town name and the two pieces of information. Okay, and we should be able to check it against this and get all our answers, presumably. All right, so when this is all said and done, just gonna steal this guy. Say, check our work. Just have another loop here. And we'll tell Curtown to display Dijkstra's. So just go back through all the towns after we've updated all of them and tell them to display Dijkstra's. Let's see, did we go through all the towns? So Mequon is 0. That's correct. Cedarburg is 8 from Mequon. 8 from Mequon. Grafton is 10 from Mequon. Grafton 10 from Mequon. Port Washington is 17 from Grafton. It's weird that we have a 7. Oh, because I need to add 2. No? Yes. Small bug. When we update it, inside I'm lost. In here, I can't just tell it your new value is the Kerr Road's distance. It's got to be the Kerr Town's shortest distance plus the Kerr Road. That's the new value of this guy. Those two things added together. Otherwise, I'm always just saying, hey, the actual shortest distance to get here is the last road I took, not the last road I took, plus all the other roads I had to take to get to that previous town. Saukville, I feel like there's a better chance of this being right than my math. I had, well, Saukville was 18 Grafton, that's right. Port Washington was 17 Grafton, that's right. Belgium 25, Port Washington. Belgium 25, Port Washington. Fredonia 23, Saukville. 23 Saukville. All right. So looks like that pretty much solves a single pass through Dijkstra's for a given start town. So now what you could do is if you wanted to have something for all possible start towns, you could have a array of maybe array of structs that has these 2 values in it, or array of objects that keeps track of a shortest distance and the previous town. Maybe it's in a third thing and what that start town was. So it can keep track of that, you know, for Mequon being the start town, Grafton is this, but for Saukville being the start town, Grafton is something else, and that kind of stuff. You can keep track of that information for all possible start towns. So now you should start seeing that, okay, this gets fairly complex, and you're starting to, well, it's not necessarily fairly complex. When we look at this code we just wrote, I mean, this was just checking our work. So really, our algorithm was this stuff right here. And then we just wrote a couple of short abilities into our objects. So the actual algorithm for this isn't overly bad. It's just a little tedious, right? Not the end of the world, but we can imagine that if you're having to do this for every possible start location and keep track of all these different pieces of information to handle all the different scenarios at every single town, that's going to start taking up a lot of memory very quickly. And the more and more towns we add, the worse it gets. Does that make sense? So that kind of puts us down that path of that traveling salesman problem issue, where we believe that this could get out of hand pretty quickly. All right, even though we've just made a single pass. So we've gotten the shortest path to each town from a starting position, and now we know which direction to go, and we can certainly write some code to walk backwards and say, okay, well, then if you're going to Saukville, what towns should you go through? We could just walk backwards and follow the yellow brick road if we wanted to. We're not going to do that for right now. So I will put it on here. Dijkstra's code, something like that. Okay. So questions about that guy? All right, so let's keep cooking to our next thing. Just in case I didn't mention it last time, I think I did, but I'm just going to keep reminding you till we get into it. I put the link up here. Next week, Tuesday, Wednesday, Thursday nights from 5 to 8 p.m. in the collaboratorium outside the makerspace in the Plaster Building are the senior seminar presentations. I beg you to come to some or all of those. I know it's a big time commitment, so it's not necessarily reasonable to come to all of them, but if you chose to come down there and kind of work on homework and stuff while they were going on, to have an audience, that would be nice to support the seniors and maybe pay attention to some of the presentations so you can get a feel for what you're going to have to go through when you take the 491 class. Again, that's next Tuesday, Wednesday, Thursday nights from 5 to 8 p.m. down in the collaboratorium. So put that on your calendar if you would not mind. Okay. So next thing that we want to talk about, and I'm guessing this is probably going to be the last thing that we're going to end up talking about in the class, since next week's our last week, but we'll see, is the concept of compression. So compression is used often in all sorts of things, right? You know, even if you're not even aware that it's being used, if you've ever had you know, cable TV or dish direct TV or any of those things, you know, before streaming, and I promise you streaming uses compression, but the example ends up being better. So how many of you have ever had cable or dish network or direct TV? Okay, so you've had one of those things, and you always had to have a box, right? You had to have the direct TV box or the cable box. What did that box do? Now, more recently, they have like DVRs in them, right? But even before the DVR, you still had to have the box, right? So what does that box actually accomplish? What's that doing? Must be doing something, right? Some kind of computing crap, all right? Now, you're watching your TV shows, and this became even a bigger issue as we went from standard definition TV to high definition TV. And we don't even think about it as high definition anymore now. That's just called TV, right? if it's not in high definition, it might as well be radio at this point. But there was a point in time where you had standard definition and you had, you know, a handful of high definition channels that were really, you know, cool to look at and that kind of jazz. But when you have a, let's say, a high definition channel, so let's say it's full HD. Full HD is 1920 by 1080 pixels. So that's 1920 times 1080, which gives me 2 billion. Equals 2 billion pixels. Now, pixel's a little dot of light. So let's say that we're dealing with, I don't know, 24-bit color, something like that. You know, so we would have 2 to the 24th unique colors in the palette that we could represent, you know, to give nice, vibrant colors. There is higher definition that even if we say it's 16-bit color, still going to give us a big number, but let's go with 24-bit color. So now we're going to have times 24. I'll drag this down. So that gives me that number of bits for a single frame. Or if I want to divide that by 8, that's bytes. Divide it by 1024, that's kilobytes. Divide that by 1024, that's megabytes. So 5.93 megabytes for a single picture on your TV. Okay, now many of our, when you're watching standard TV, you might be watching at 24, 30 frames a second, something like that. Now that's even higher than that, but let's just go off of 30 frames a second for no good reason. All right, just kind of giving us a guesstimated thing. So that means we have 30 times 5.93 gives us that. So 177 megabytes per second is how big a TV signal is for every single second that you're watching it on TV. All right. Now, we think about our internet connection. Your average person today has, if we're thinking about, because this is true for streaming too, right? You're streaming high definition, the same thing's true. So let's say you have 200 megabits per second internet connection. 200 divided by 8 gives you 25 megabytes per second. So with 200 megabit per second internet, the most you can download is 25 megabytes per second. You need to be able to download 178 megabytes per second. That's a problem. That's where that box comes in. So what they do is they take these bits associated with that picture and they compress it somehow. Various compression algorithms that say, yes, the data in its raw uncompressed format is this big, but we're going to find an alternative way of representing it that is what's called lossless. So you can still recreate the data at the destination, but it can be transferred in a smaller pack. Think of it like a zip file, right? When you zip something up, a compressed file, you send it somewhere, you have to unzip it on the other end. You don't care what the algorithm was in the middle that actually did the compression, just that it was something. All right. So now that box that's on top of the TV for your cable or your DirecTV or your Dish Network, whatever, or the computer that's built into the smart TVs now, if you're doing streaming or whatever, or the computer that's built in like your Roku stick or your Apple TV, whatever, they're all doing the compression. Well, they're doing the decompression since you're not broadcasting stuff, you're a recipient of stuff for them. All right, because we see that 177 is not going to cut it. Even if you have gigabit internet today, so let's say it's the fastest consumer internet that you might be able to get today, that could only do 128 megabytes per second. You're still not going to keep up with high definition TV signal to deal with it raw. All right, so we need to have the ability to compress and also decompress. So what we're going to look at on Monday is something called Huffman coding. And we're going to start off by doing something called a character frequency table, because Huffman coding uses the current state of the data to generate the codes that will be used to compress the data. That information will then be necessary on the receiving end to decode the data, decompress the data. You'll have to know what the initial frequency table was that was used to compress it. Okay, so we'll come back on Monday and we'll start talking about that and get through it. On Wednesday, we'll talk about the final, probably, or Friday, one of the two, probably Friday. The final exam is the week after next. I'll do the usual. I'll put it up on like Monday. You can take it anytime you want during the week. I'll put up the set time that the exam was supposed to be. I'll make sure I'm sitting in front of Slack during that time in case you have questions or whatever. If you want to come to the classroom, I'll be in my office. It's up to you, but you can decide what, from a time management perspective, what's the best time to take it. Questions, comments, concerns, bribes? All right, I'll see everybody on Monday.